Why don't we go ahead? Perfect. Okay. I think we're good to go. So let's go ahead and get started, and then we can let some people trickle in if they join. So if everyone could please mute themselves, Jess will get better audio that way. Okay, so tonight it's my pleasure to introduce you to John. John is the president and principal engineer at Doc 13 Engineering and founding partner at Fuel Biomedical, a medical device development company based in Calgary. John's a local industry veteran and entrepreneur, working as a mechanical design engineer and project leader, specializing in new product development, mechanical system simulation, regulatory clearance, and device and design and development since 2000. So he has diverse experience working directly with businesses, managing technical teams, and designing equipment for medical device applications, aircraft ground support, oil field compression, downhole tools, and consumer products, and has helped clients turn their ideas into profit-generating technology. And so a fun aside is that John actually works with my company, FredSense, on helping us develop some technology that I think he's going to talk a little bit about tonight. John holds a Master's of Applied Science in Engineering, Biomedical from the University of British Columbia, and a B.Sc with distinction in Mechanical Engineering from the University of Manitoba. He's a professional engineer registered with APEGA and is an Avenue Calgary Top 40 Under 40 alumni. So tonight, John's going to be talking to us a little bit about 3D printing in medical device design, really interesting topic. And so 3D printing has evolved in the past decade from a specialty tool for academic research to an ever-growing industry of on-demand prototype and additive manufacturing service providers and manufacturers of desktop devices for professionals and makers. So John's going to review some of the history and evolution of 3D printing and look at different types of printable media. And we're going to see some of the different applications of the technology. So I'm going to pass it over to John. If everyone could just stay muted for the duration of the presentation, we'll have lots of time and to ask questions. So with that, I'll turn it over.
Excellent. Thanks very much, Emily. That was appreciate the introduction, and good evening, everyone. Just Emily, if you can give me a thumbs up still, the screen showing okay. Excellent. So yeah, thank you for that introduction. I do have a history working in the medical device industry, and which is unusual for Calgary, but I've kind of forced myself into that position because I just want to do it, and I really like being in that space. So that's why I started Fuel Biomedical about 3 years ago now with a colleague of mine who's also working in this medical device space, and worked in consulting engineering and development before that time. So tonight I'll talk to you a bit about my experience with 3D printing for medical device design. I'll show you, just click here. Oh, Sheila, I'll ask you to just mute yourself, please. So Sheila, got you on off mute. Thank you. All right, so the agenda for my talk tonight, I'm going to give you a little bit of background about 3D printing, and then I'll go into some example projects of things I've worked on and where I've used 3D printing in the past and even today, including the project that Emily alluded to. And then I'd like to talk to you about medical use trends. So trends in the medical device industry, and then we'll have some questions afterwards. So if you have some questions, please jot them down, put them in the chat, and we'll try and get to them all at the end of the presentation. So let's jump into it here. So what is 3D printing? I don't know how many people are familiar with it. It's pretty common in the news today, but basically if you think about traditional 2D printing, where you deposit ink media on a two-dimensional surface, 3D printing is pretty much the same thing, except you add the Z-axis to your print coordinates. And instead of printing with ink, you're printing often with plastic, but there's many other materials. Some of the diverse types of 3D printing that are available, I'll list off a few here, and we'll get into the details later. These green ones in particular, I'll talk to you about. But stereolithography is one of the big ones. Fused deposition modeling, selective laser sintering, digital light process, multi-jet fusion, polyjet, direct metal laser sintering, and electron beam melting. These are all various types of 3D printing where you're taking different media, be it plastic, biomaterials, metal, and you're printing out a three-dimensional object with them. For a bit of history, it all really started with this guy, Chuck Hull, who they call the father of stereolithography, and that was the very first type of 3D printing. I'll explain it in the next slide, but just to give you some of the history of it, he basically was working in a company where they were curing tabletops. They put resin on tabletops and cure it with UV light, like a furniture place. And he thought there might be an application for this in producing three-dimensional objects. So the company, it's literally let him work on weekends and evenings in their space to kind of tinker with this idea. And in the early 80s, in 1984, actually, he patented this first stereolithography device patent. He actually coined the term stereolithography and went from there to start a business about 3 years later called 3D Systems to try and commercialize 3D printing. And it's now one of the giants in the industry. And the total industry for 3D printing is estimated to be a $3 billion a year annual business, and it's growing. It's been growing about 17% every year for the last 5 years, as I think we've seen a lot of the desktop models become more available and more maker space type inventors want to get their hands on it. So that's where it all started. To just give you a little idea about stereolithography and how it works, basically he developed a system using photopolymers. So they're acrylic-based materials that start as a liquid. It kind of looks like a hand soap or a liquid hand soap or a shampoo when you see this stuff in its native form. It's got about that consistency. But when you hit it with an ultraviolet light, it turns solid. So if you put a tray of this material outside on a sunny day, it would be a solid block at the end of the day. But if you have a laser to control your light source, then you can selectively target the areas that you want to harden within that soup of photopolymer. So a laser light will control the XY axis of the printing, a UV laser, and much like the XY axis of a print head. And oh, sorry, just got a little more background noise there. I'll ask Leonard to mute. So you get the laser light control on the XY axis, and the height of the is controlled with a traveling platform. So basically, you can see in this example here, the laser will make a layer of material, and then it moves it up incrementally and makes the next layer, and moves it up incrementally and makes the next layer. So you'll get about a print can vary from 100 layers to thousands of layers, depending on how thin you want the layer to print, what your machine is capable of, and how much resolution you want. So basically, you can print the three-dimensional object by controlling X, Y, Z. And this is how the 3D printing started as stereolithography, but then other ones followed on to that. People got the idea of being able to lay down a bead of plastic instead of using a resin. So you can, with this style called fused deposition modeling, or FDM, you take a plastic filament. So it's an existing plastic like you'd see in commercial plastics that you have in your products in your day-to-day life. It's that same kind of plastic, except it comes in a filament, and you melt the filament in the print head, and then the print head moves XY instead of the laser. So it's actually laying down a bead of hot plastic. So this has also become a very popular style of 3D printing in the world today, with especially these maker spaces like to use it because it's more readily affordable. The machines are more affordable, and the filaments can come in different styles of plastic. So you have a lot of choice. So a lot of desktop type of makers will use this. One of the other advantages of FDM is that you're not as limited in the size or the volume of the print volume that you can print something. As long as you've got a large axis machine, you can print larger objects. So you can print larger objects with SLA printers, but the printers that can, if you're comparing sizes, if you could print something the size of a basketball on an FDM printer versus an SLA printer, the SLA printer would probably cost 10 times the amount of that FDM printer to give you the same size and print volume. So that's how FDM works. Another type of print that came out of this that's really highly specialized is selective laser sintering, or SLS. And there's other types that are metal based, but this one's a really cool design where you can take a powder of a metal like stainless steel or titanium or some other metal, and you apply a laser to it, which instead of curing it, it actually melts the material. So you get melted fine powder of material to create your 3D object. But it's the same principle. So in this little photo here, you can see this impeller blade. It would have started in this powder slurry, and you print on it, and the deck drops down, and it just keeps printing it. So at the end of it, you have this cool. You're like an archaeologist where you get to brush off all the dust, and you see your part emerge from the powder. But it's this one. If you thought the SLA one was expensive that I just talked about, if you had a basketball-sized SLS printer, it'd probably be 10 times the SLA printer, so 100 times a fused deposition model printer for cost. So these things can get pretty expensive, in the hundreds of thousands of dollars. And SLS printing requires special rooms, clean rooms often, or special equipment, because this powder is extremely fine. So people using it, they have to wear respirators. They'll have to put on special gowns and equipment, because the powder's quite toxic if you inhale it. But they're doing some really cool things with it, especially in the medical device world, which we'll see a little later on in the presentation. So how do you choose what type of 3D printing you want if there's all these options available? And really the 5 major considerations are: what's your budget? What are the mechanical requirements of the part? What kind of cosmetic appearance are you looking for? Are you looking for a specific type of material that you'd like to test? And also, what's the geometry? So this basketball analogy again, can you afford it? So in this little photo here, you can see the same printout of the Statue of Liberty done in SLA printing versus FDM. There's quite a quality difference between these two as far as the print resolution and often the strength of the material. So you can see these fine lines of the printing in the FDM. That often leads to areas of where the structure is weaker, and you can shear off in these layers. If you're trying to test something, some mechanical properties, you might not be able to do it as easily with FDM, whereas an SLA is a little more homogeneous and gives you better mechanical properties for testing. So that's a bit of the overview of what these different types are, the kind of the major. I'd say these 3 I showed you is like 80% of what the 3D printing is today, and the other ones are specialized for different applications, but it's used in all kinds of industries today. So I'll give you some example projects of stuff I've worked on. So Emily said I've been working on medical devices since 2000, and here's one of the first projects I worked on in 2001 even. Let me get my little laser pointer going here. So this guy is the Explorer 1700 digital X-ray imager. So it was one of the first kind of digital X-ray technologies. It was developed right here in Calgary, and I had an opportunity as a young engineer to work on this project. So you can see there's a lot in it, and there's a lot mechanically going on inside, electrically going on inside. But this was at the very early days of 3D printing commercially. It was available, but it was becoming more commercially available. And we were actually able to print some of these elements that you see here, these design elements like the buttons and the cowlings and things. These big ones were actually made of fiberglass, so not those ones, but some of the smaller ones for test it up. Started doing 3D printing on that. And that kind of gave me the bug for wanting to do 3D printing as often as I could moving forward. So as I went through my career, I always tried to get onto projects where I could do 3D printing. And I'll come back to a few examples later on, but I'll bring you up to speed with some current projects and how I'm using 3D printing today. So this is the project we're working on right now called the X-Leg, and it is a crutch replacement. So well, this guy's not a good example because he's standing there with crutches, but as soon as he left the hospital, he threw them away and started walking around on this X-Leg. So it's kind of a prosthetic type device, an assistive device, and people wear it on their legs here. Here's another guy we had, patient that used it just this fall. We had him in one, and he had a total knee replacement surgery and was unable to put weight on it. And in fact, Emily, I think you know about the X-Leg as well, because you got the chance to wear one for a little while. So you get to see here's some of the production stuff. So we're into kind of a production. We're into production now, where we're making about 10 of these a month in batches of 10, and we're selling them across Canada and in the US. So when you're making 10 of them, that's not really, it's good for this kind of work where we're doing aluminum and welding and good for that kind of batch work, but it doesn't really lend itself to getting a production mold made in injection molding. So to bridge the gap, some of the parts on here we do as 3D printing. So this guy is the foot cap or the toe cap, and we put this one on the very bottom of the toe to kind of keep out the dirt and muck, and it's a bit cosmetic too. So up here you can see one of the first iterations of it where I spray painted it gray, but this was the very first one. I 3D printed this cap just to have something to show as a demonstration. And then we actually liked it so much, we started using it as part of the production stream. So we tried another version of it with a different material. This is called the tough material that works on our 3D printer, and didn't quite like the way it was performing in colder weather. So tried switching to this material over here, Gray Pro, and eventually we went to this black material. So you can see how it's kind of evolved. There's 4 iterations just on this screen, and now we're using the black material as our foot cover. So this one is directly printed on an SLA 3D printer and used for some production work in our device here. Another way we're using 3D printing on this unit is we're making the foot itself, so the grip on the bottom of the foot, which you can see down here. But we're not 3D printing the foot, we're 3D printing a mold. So we can mold out of a soft rubber that's good for the sole of this unit to be molded in this casting. So we take our 3D printer and we make these molds and cast the rubber into them to get this output, which we then can screw onto the bottom of the foot. So that's another way we're using 3D printing for this kind of bridge production. So we're happy to get these units out in the world, and we're seeing them, people are trying them on and using them and liking them. Emily, I think this is the one you got here, the bronze one. So that's great. And speaking of Emily's project, this is her company's product, the FredSense detector. And one of the way that this product works is you put water samples in a cartridge that goes into this slot, and then it'll take a reading for you automatically in the field. So instead of sending something away to a lab and you can do it immediately in the field. But the cartridge design that they have for this was a bit labor intensive for them. They were actually making it the same way I was just showing you, where they have a mold and they're pouring it into the mold and making these cartridges by hand. And so we wanted to start developing something that would bridge into injection molding a cartridge for this device. But at this point, we don't need to injection mold them, so we can do the same kind of thing where we can have can make them on our 3D printer and have 3D printed cartridges. So this is a good example because I can walk you through exactly the process of how I do the 3D printing. So we start with a 3D model. So 3D modeling software, we can create this, this object in three-dimensional space, and we download it into this software over here, which sets it up for 3D printing. So this is a step between the model that you create and then you put it in the software to create this 3D print file. So what you're seeing here is it creates a raft of material. The grid here is the base of the platform, and the raft of material sticks to the base of the platform, and then you build it up layer by layer across here. And there's different considerations. You see, maybe you're wondering why it's printed on this funny angle. The way that the printer works, if you print it flat sometimes, it creates a suction cup, so your part would stick on there as you're printing it. So you have to put it in different orientations to make sure you get a nice clean print out of it. So that's why this guy's on this angle. And then there's little rafts and supports are built into it to help as it's being printed. But after you're done, you break those off and clean it up. So this is the printing process you see here. You can see this tub of gel is the SLA acrylic for printing. And these are some of the objects that are printed on the platen. And it prints it upside down because it starts from this layer and draws it up and out. So the laser is working in here as you do your layers of material, and it pulls this guy actually upwards and builds the layers one at a time this way. So eventually you reach the tip of it and then the part's done. So this shows you, I've pulled it out of the unit and it's right side up so you can see what the parts look like. And here's the two main kind of components of the printer, which are the tray for the resin and the resin tank itself. So you can see in this picture, it kind of looks like a shampoo. But in case you didn't really see it, I've got this cool video to show you the actual in process. So you can see the laser starting here, the UV laser. It's burning in one layer. Then it will lift up the platen. It sweeps a layer of the gel across, and then it puts it back down incrementally, and it's going to do the next layer. So it prints one layer at a time like this, depending on the size of the part. These prints that you saw were about 1,000 layers in the way that it was oriented. So it takes a few hours to print something like this. And that's the speed of it too. After you're done with the printing, you have to wash the parts. So they've got that, they come out like a newborn with all the goo and gel on them, and you have to clean them up. So you put your newborn baby parts in the washing station, and it looks kind of like a deep fryer, but it's actually full of isopropyl alcohol. And isopropyl alcohol, if left in there, it'll dissolve these parts. But when it's in its goo, the slick goo on the outside, it just washes it off, so you have a clean part after that. So you put this in there, it automatically swirls the IPA around and cleans the parts off. And then once that's done, you put them into the curing station. So the finishing of all these parts requires that you put it into, set it in UV light to harden the material. So it's gone through and it's made all the layers, but to fully realize the mechanical properties of these units, you have to put them in a cure station. You can put them in direct sunlight to cure, but that's not always reliable, even though Calgary, where we are, is pretty good for sunshine. It's not the best to leave your parts out in the winter. So what we do is we have this curing station, and it actually heats it up as well. So there's depending on the print that we're doing, you have a specific temperature and hold time that you cure it at. So this one, the clear, for example, it heats it up to 60 degrees Celsius, and it holds it in the UV bath for 30 minutes to get a full cure. So this little disc rotates around and it gives it a full blast of UV light. So once that's done, then we do the post-processing. So the parts are done, but they come out with this rafting on them. So you mechanically have to go in and snip off all the rafting and clean it up and do some sanding possibly. So one of the things we try and do when we're printing these parts out is you want to get that orientation right in your print deck so that you don't get this suction cup effect or other hazardous effects, but also you don't want to do a lot of cleanup afterwards. So you're trying to orient it so that the cleanup's minimal and it's not affecting some of the target zones here. So you can see once the part's cleaned up and the rafting is gone, we've left this surface exposed and nice and clean so that we can put a little adhesive sticker on it. So we don't have to go in here and try and clean up the rafting because it's on the top and it's doesn't have the rafting on it. So this is what the parts look like at the end. And you'll notice here that one of the parts is gray. And that's because we have different material options to print on the same 3D printer. So if you change the resin tank and you change the cartridge out, you can put different types of material in here. And the clear is a nice material for its structural stability and of course to see through it, which we want to do to make sure we can see the sample is in this cartridge. But we want to have a stiff back on it to hold our little electrode. There's a wafer electrode on the back of this that has to be held stiffly. So we have this gray backing on it of a different material. And one of the other things about this material is it has a bit more flexibility than the clear. So we're working on this design now where we had started with a version that would screw together with hardware. This one snaps together with just the plastic of the device itself. So that'll be much cheaper and easier for assembly. So I'll show you a little snap fit video here. You can see this video where for the first time, I'm taking our two pieces and I'm pushing them together by hand and they snap together. I don't know if you can hear the satisfying snap, but trust me, it's there. And now the two halves are snapped together and we are not able to pull this apart. So I went and tried here to pull it apart and you'll see that I can't get it apart. So that's what we want. We wanted the thing to stick together and not come apart once it's snapped together. And there you can see the little electrode and the adhesive gasket. So now that little cartridge is ready to use, we just have to put a cap on the top and then it gets injected with the samples and the electrodes will read the samples in that detector, which is really cool. So let's see, what are some of the other projects where I've used 3D printing in medical applications? Another one we're working on, it's called a Lift2Go. It's a wheelchair lifting device. And you can see that it's got a lot of metal in it and a lot of hardware and things like that. But we actually did use some 3D printing to print elements of it. And one of the good examples that I had from this unit was we had a lock geometry. So if I go back here and show you, this has a drive mechanism here, which is a mechanical drive, but it also at the front here has an overspeed. So this is one of the requirements for wheelchair lifts is that if something happens with the main mechanical drive, this overspeed prevents it from running away down the tracks. So that was a compliance issue. So what we did in there was put like this ratcheting device. And you can see when I start this video on the right-hand side, this was the ratcheting. So we rotate one way and we'll lock up the other way. But this geometry was really tricky to figure out. So we ended up printing out our geometry with the 3D plastic and tried a couple of variations of it before we committed to the design. So we knew this thing would work by doing our 3D printing, and the cost was negligible. Once we got that in place, we could print out our full steel version of this thing. So this device was functional. We knew it would be functional, and that our braking device would work based on the 3D printing. So that was a lot of fun for that. Some of the other projects I've worked on in the past. This is a consumer device for light therapy, and was sold online. And actually, one year I went to Costco and I saw a big pallet full of them. So that was kind of cool to see a device out there. But this guy was a really good candidate for 3D printing because working with our industrial design colleague, we actually had 3D prints made of the shape of it before we did any of the internal design work on it. So the customer could feel how and look at how a bunch of these would behave as a device before we even got into the nitty-gritty of the design work. So they kind of look like bars of soap, but they got the idea across very well because we have 5 different shapes, and the subtle differences between the shapes were enough to pick one. So we went from there to produce this, and even some of the elements of the early prototypes were 3D printed. So it's a great way to quickly iterate through designs to show people what you're thinking and what the device should do. And that's one of the big advantages. On here, this is a training device for surgeons to test, to practice surgery on the knee. So the bone itself is not 3D printed, but the early molds of it were. So we were able to make a 3D mold of this, and then put a cast of silicone around it, and then use that to make the final mold here. And this is a proprietary bone material, which feels like bone. So it's hard on the outside, but when you drill through it, it plunges really quickly. So for new surgeons, it really emulates the training and feel of surgery. So use 3D printing in that development as well, and even in the mold making around these skins and ligaments on the top. So the device itself, we didn't do a lot of 3D printing to sort this guy out, but this guy up here we did. And this here is a really interesting device. So it's a image guided surgery for drilling into bones for doing intermedullary nail placement. So intermedullary nail is a long nail that goes down the middle of your femur. If you've broken your femur and you can't fix it conventionally, you can put this long support nail through it. But at the end of it, there's 2 little holes, and you have to hit them basically blindly. The doctor has to know where the holes are, and they have some external jigs and things. But this guy was an attachment that you could put on the drill, and it had a little screen there with a target on it, like a little bullseye, and it would tell you when you're in the right orientation, and you can plunge through with the drill and hit the target. So this unit, the housing for this was 3D printed with a material called Ultim, which is a fused deposition method printout, but a high resolution one. So pretty expensive printers. And the other cool thing about this Ultim material is that it can be sterilized. So once it was printed, it could be put in a steam sterilization unit, and it wouldn't warp or melt like some of the other plastics would, the conventional plastics. So these are just a few examples of some of the medical devices that where I've used this 3D printing technology. So what are some of the trends in medical device 3D printing that we're seeing today? You saw a few examples here. A lot of the trends we're seeing are things like surgical planning and guides for surgery, training tools like that bone model I just showed you. People are also using 3D printing for custom surgical tools, bioprinting for transplants, and prosthetics. So I'll show you a few examples of these things. For example, with surgical planning, you can use X-ray and MRI scans you can isolate the 3D elements from the scans and print them out in 3D like this. So surgeons are using these to help visualize the area before they go into surgery, or do some preoperative planning, or possibly put some jig together that will help them with their surgeries. So they can do a lot in advance before they even take the patient into the OR. And that's one of the big elements of surgical planning. We're seeing that now. There's also, taking it a step further, people are using this technology to make personalized cutting guides for surgeons, for the patients and the surgeons to use. So they can do this 3D scanning, MRI scanning or X-ray scanning, and get a 3D model of the person's bone, and then build a custom drilling or cutting jig that will fit on the bone. So when they get into the surgery, they have the landmarks already personalized to these people, and they put this jig on there and they can do the cuts directly. So this is an example of a drilling guide on the knee surgery. And you can see here, this would be a cutting guide, for example. So there's a reusable stainless steel cutting guide, and then there's a custom printed jig basically that fits on specifically onto the person's bone. And then they would go in the slot here. They take an oscillating saw and they put the saw in and they cut the top of the femur off to do the implants. So this is a really interesting new application that we're seeing in the last couple of years. And there's even some companies that that's what they specialize in, is they will just print surgery ready personalized guides. Beyond that, of course, custom printed parts, new parts for you. These are some of the wilder examples I found out there. A custom printed skull for someone who had they had the bone of their skull had deteriorated, so they were able to print basically the top of their cranium and surgically implant that. So this was an application of 3D printing that took it from scanning to cutting guides to actually leaving it as an implant in the person. Here's another application you can see of that selective laser sintering metal with a titanium rib cage and sternum, basically printed up on that would go into the that would be implanted to replace someone's damaged sternum, either through disease or trauma. And in this case, they printed the whole rib cage so they could check how they were going to install it. So you can see that there's a series of drill hole or screw holes along here. That's what these holes are. They would check the fit up on this model and then be able to put the bone screws in intraoperatively. And we've also seen some applications where people are printing soft tissue implants, and this is a biotissue type of implant where they create a matrix of biological tissue, and they can infuse it with cells to grow. Basically, someone will grow a new ear, so you install this matrix. Implant the matrix in their ear, and then their tissue would grow into it. So these are some of the applications we're seeing bridging from where we're starting with the implants, or from scanning into implants. Prosthetics, of course, that's another interesting application of it. And you can get artificial arms and legs, and people are really taking it to customization type extremes. This is a titanium leg that's printed up. People are putting their own patterns on it. There's now people are, rather than hiding the fact that they've got a prosthetic leg, they're taking it to the next level. And this is a fun one here. They're wondering about our chicken. He's got prosthetic feet. And that was printed here at the University of Calgary, at Veterinary School of Medicine. They were doing a little experiment with 3D printing, and it got a little out of hand, and it made the national news a few years ago to have this chicken with prosthetic feet on. So there's all kinds of applications for prosthetics. And back to our friends, 3D Systems. This is kind of the direction they're heading in with all their applications. Lots of medical applications for implants and training, and patient-specific guides. And one of the other areas, of course, they're getting into is bioprinting, which is a new area of really taking the technology further, where rather than printing with metal or plastic materials, it's live cell tissue they can print with. So this kind of trachea was printed from live stem cell tissue and cell tissue, and could be implanted surgically in the body afterwards. And another cell matrix over here showing some blood pathways in the lung, for example. So there's all kinds of really intense type of bioprinting that's happening. Hugh from your group sent me a neat article last night where they're talking about doing this in 0G, so that the printing matrix, you could get away from this kind of sloppy collapsing matrix of this soft material. You still have to have the rafting and the supports like I showed you on the prints that I do, but it has to be of a biocompatible material. So with looking into space now for doing this, that would give you the ability to print more complicated objects that wouldn't require rafting. But I did promise you that one of the things we look at tonight, and the last thing we're going to look at tonight, was printing from different plastics from metal to meat. So even as late in the game as this August, the Osaka University in Japan printed its very first Wagyu beef to simulate food. So they've got this really wild looking printout here, and no one's tasted it yet apparently, but chemically it's the same as the Wagyu beef. So this might be the future, not of medical engineering, but of 3D printing. There's all kinds of applications coming down the pathway, and it's just getting bigger and crazier. So it's a fun time to be involved in 3D printing, and especially in medical device development. So that's all for my talk tonight. Thank you for your attention, and I'm available here for questions if anyone wants me to go back to a slide or look at some other elements. That's a question in the chat. Okay, thank you. All right, appreciate that.
John, maybe it's Hugh. Maybe I can just ask a quick question to kick
Yes.
it off. But you know, we're listening to the COP26 and the climate issues, and they've been quite silent about agricultural emissions. But I'm just wondering, with 3D printing of meat, is that something that could help in the long term, I guess, reduce the emissions from agriculture and CO2 and methane gas?
Yeah, absolutely, and it's one of the major driving factors that they're talking about for this, for looking at printing meat, is that it can reduce. They're printing it from other proteins that are more readily available, grown. They can be grown in a lab, and they're grown with less power requirement. So that's one of the requirements. And I think particularly that example, the Wagyu beef, it's known as a delicacy, and it's highly sought after. So they wanted to show that could be, that could be emulated as well. Like anything, it's not just going to be some disgusting gruel. It can be like a high value material, and we're seeing that a lot across 3D printing. People are using it for high value components like aerospace, rocket engine components, things that are hard to make conventionally or otherwise. That's what's happening. But yes, to answer your question about the meat, that's one of the major driving factors behind it. And I think one of the reasons people would actually get behind it in the long run is people would buy it would purchase it for that reason.
John, perhaps I can throw in a comment.
Yes.
So now that the deposition method is now being used in civil engineering to 3D print concrete.
Yes.
And so I was reading an article where in the Netherlands, they had 3D printed the base for a house, and they'd done that in 2 days with 2 men, where it normally take 5 days for 5 men to put up the formwork, cast the concrete, blah, blah, blah. So they'd taken the number of man hours down from 25 man days to 4 man days with this 3D concrete printer. So yeah, it's not just the exotic materials, it's getting into the really crude, heavy stuff that we'd use in construction.
Yes. Yeah, absolutely. I know the one you're talking about, and they used, I think they used kind of a robotic arm to do the printing.
Yeah, just to use a robotic arm going across the site. Yeah.
So
Sorry, I was going to say, in your in those printing of those tissue scaffolds, is it polylactic acid, or do you know what it is that's being produced there?
Oh, I don't know all the details there, Nigel. I just think it's a cool technology. But
Yeah,
that's definitely the high end of 3D printing, because it's much, like I think about the problems I encounter with known materials, and I can't imagine what it's like printing with the biological materials. So very interesting.
And it was just interesting to me that it had gone that far, because tissue scaffolds are pretty darn difficult to do, and 3D printing, when you think about it, is an obvious choice.
Yeah. And I think that's why it's still highly specialized in that regard.
Yeah.
I mean, we're at a stage like the 3D printing, really, like I said, in the last 5 years, it's become commercially available for like under $10,000 was kind of this break even, or this breakaway point where suddenly people would decide to buy a printer for themselves, for their desktop or for their small business. But before that, and even myself before that, I would go out to the larger print houses that were set up with these giant machines and print things there. But now I can have this machine in my own business, which is
it looks fascinating. I'm glad you're enjoying playing with it.
Absolutely. Yeah, I've got things printing right now, even as this meeting's going on, so I couldn't stop.
Good one.
Yeah, I see a question in the chat here from Alan. Reading recently about 3D printing of aero engine parts, the issue was microvoids forming that were really hard to find through inspection. Is product inspection an issue in general? Yeah, I think that's one of the reasons 3D printing is still, it's not 100% used commercially. People still prefer to go to the traditional methods for larger scale prints, or for larger scale production. But we're finding that the materials are, when they're used in the right application, they can be pretty stable. But things like that, yeah, aero engine parts are high stress, high risk applications. I think they have to do a lot of they can still do lots of material testing on those, or you can still do the normal kind of annealing and tempering processes on these materials, and that's what happens as well. One of the slides you have a heart picture. Is that a 3D printed heart? It was a 3D printed heart, but just a model, so a training model, or it would have been for surgical planning. But there is research going on right now where people are trying to print organs like hearts, muscular organs. Yeah. Would it be possible to print a whole house? Yeah, that's exactly what had happened in the Netherlands. It's kind of a funky looking house, but people are now living in it. I think they had to build the roof separately, so it was a standard kind of roof, but the walls were 3D printed, and people have moved into this house.
What's that house made of, plastic or concrete?
It's concrete.
Yeah. Oh, you did printed it with concrete, yeah.
So they had to you're the civil engineers, so you tell me how you prevent it from slumping, but they were able to extrude it basically the same way the filament printer worked, and they built this layer, just built it up like a cake icing, really. It just kind of built it up and up. So same idea.
Yeah, for those of you who are Brits and know about HS2, they're using concrete 3D printing and part of the HS2 construction as well.
Yeah, I think it's great for one-offs and prototyping. That seems to be the direction that you were taking this, John.
Yeah, and even small production. So the example I showed you for Emily's project, we can print, several hundred of them a month. But as it gets into more production, the labor cost to do the post-processing becomes prohibitive. So then you want to go to injection molding. So there is a break-even point with things like paying for the molds versus just paying for the material and the print time. So
it brought back memories when I was a student apprentice working in a tool room where we built jigs for motor press things. And the money really wasn't building the jigs. Once the jigs were set up with some exactitude, then you could stamp out millions of parts.
Exactly. Yep, exactly. So this is different where, now you've skipped the jigging process and you can just print the part directly. So it is a different economic return on investment, but that's what we're trying to play with here, especially on this project I showed you for Emily, where there is this point where scales reach a certain point where it makes it worthwhile to invest in the molds and the jigs and then go to injection molding. But the real advantage for us now is we can quickly iterate through different design ideas and change the mold or change the part and come up with a real optimized part quickly. And you can imagine, Alan, trying to do that with jigs and molds. You really have to know what you're doing. Like, you don't want to change it. You don't want to be sketching in metal, as one of my friends called it.
It's also fascinating when you're almost customizing these tools, these jigs for surgeons. And I wondered, do you really go to the lengths of making them for left-handed or right-handed people, or is there a difference in the setup?
You absolutely could. It's up to the surgeon, and that's what's really neat about that approach. So, yeah. I see Robert had a question in here. Can approaches like SLS be used with alloys? Oh, yes. Are there any issues with using a single laser strength for mixtures, different thermal expansion coefficients? Typically, it's used for homogeneous alloys. I've done a 3D print in stainless 316, and I've also seen prints in titanium. That's typically where it's used today for those types of materials. So not too many alloys like standard steel alloys or things like that. It's really used in those kind of exotic materials. But that's what my experience, what I've seen of it. Yeah, great. Yeah, that's there's a lot to take in. It's a big field, and it's being used in every type of engineering now, where maybe not the electrical guys so much, but definitely mechanical and civil guys are really taking it on as a new way to manufacture things. And it's an exciting time. I love having this capability to think of something and quickly print something out and hold it in my hand. And it helps a lot when you're trying to explain a concept or understand a concept, just to see it, because when it's on a computer and you suddenly put it in 3D space, the size factor changes. It's crazy. Even though I know these things are like, yeah, it's gonna be this big or that big or whatever. And then it's in your hand, you go, oh, wow, like I really can't get my fingers on this thing, or I really can't get a screw through that hole or whatever. Yeah.
I think it's interesting you mentioned about the electrical engineering people, because I think they go the other way, and rather than use additive, they use subtractive. You think of printed circuit boards and etching.
Yep.
So they're going the other way and removing material rather than adding it.
Yeah. And there's even some new types of 3D printers that incorporate subtractive manufacturing. So
Yeah.
it'll print the element, and then they'll come in with another subtractive tool, like a milling head or a drill,
Right.
take away material. So those are integrated machines where you don't have to touch it, and the part comes out complete, but with both of those additive and subtractive methods built in. So it's really interesting. Yeah. GoBin, you say 3D systems, is this also known as DDD systems? No, maybe. I just know them as 3D systems. I think their logo looks like that, but you know, they focus on 3D printing. So they made the printers, the SLA printers, and then they got into these bio printers, and then they did print as a service. So order them online and the parts will be delivered to you. And it's just grown into a big monster. So really interesting for one of these origin stories of working late nights and weekends with trying to develop that technology. But that's where it all started. Yeah.
Are there any last questions for John? All right, I will take that as a no. Well, thank you so much for taking time out of your day to talk to us about this, John. It was a wonderful talk.
Great.
Really enjoyed it. And as a small token of our appreciation, we've made a donation to Operation Eyesight in your name.
Great.
We'll be sending along a certificate shortly.
Oh, I appreciate that. I actually did some project work for Operation Eyesight a few years ago, and I think we might have 3D printed something for them. So that's good. Good bookend. Thank you for that. Appreciate it.
Excellent. Well, thank you, John, and thank you everyone for coming. I hope you all have a great night.
Thank you.
Thank you.